Hello. So in chapter 6, we look at chemical calculations where we're looking at the molar mass, which is always in grams, and we can put units on it as grams per mole. And then we look at balancing a little bit where we want each side to be equal with each other. So the number of sodium on one side, the number on sodium on the other side needs to be equal, those type of things. And looking at the parentheses, because those are important, especially with the subscripts. And then we look at converting between moles of Avogadro's number and molar mass. And then sometimes you're going to get to the point where you guys are going to have to convert between moles to moles. And so there's like a fourth step, and then I also show a diagram that might be helpful for you with that. So let's get started. So we first look at molar mass, and we can reference this table. We can reference one that's online. We can reference one in our lab manual, but that is totally up to you. For NaCl2, for Na, we have a mass of 23, plus a mass of chlorine, which is 35.45. And since we have two of those, we can plug that all into our calculator, and we will get a mass of 93.90 grams per mole. We can also look at the H2O, or water. We know that hydrogen has a mass of 1, plus being there 2 hydrogens, plus a mass of 16 for oxygen. We have a mass of 18 grams per mole. Then we have Na2SO4. We can divide these into 3 steps. So we have a mass of Na of 2, plus a mass of 23 for Na, plus 32, plus 4 oxygen, plus 16 of its mass, which brings grams per mole. And on the next 3, we can do this similar process, and we should get for Li2SO4, we should get 109.88 grams per mole. We should get on this next one, we should get 463.2 grams per mole. And on the last one, we should get 180 grams per mole. And something to touch on and talk about is when we're doing these grams per mole on the abbreviations and everything, so we could write this one of 2 ways. And so when we're doing unit conversions and everything, we can write it as 180 grams per 1 mole, or we could also write it 1 mole is equal to 180 grams. I mean, if we were to do the math across, our units would cancel and our numbers would cancel, so we would just get it equaling to 1 over 1, or 1. And so it would work. It's just simple algebra that we're going to get to a point where we're going to have to multiply to get our units to cancel and get to another units that we need later. So let's look at some balancing next. So in these equations, we can see in the top where we're not balanced. Our ultimate process for these is to make sure that carbon has the same amount of carbons on the left side as on the right side. And we use the arrows to dictate the sides that they're on. So something that you could do. So for number 1, we see that we have carbon, we have hydrogen, and we have oxygen. And we have the same thing for the other side. We can see that we have 3 carbon, we have 8 hydrogen, and we have 2 oxygen. And on the right side, we can see that we have 1 carbon, 3 oxygen, and 2 hydrogen. And then we can go through and do trial and error to determine which ones that we want to start with first. We could start with carbon and try to put a number in for that one, and then see what the rest of them come out like. We could put one in for hydrogen and see what those rest of them come out like. It's totally up to you. But let's start with putting a 3 on this one, on our CO2. So if we put a 3 there, we're going to go up to 3 carbon. We're going to go up to 7 oxygen. And then for hydrogen, we can stay the same. But if we put a 4 right here, we actually take hydrogen up to 8. And then for oxygen, we go up to 10. And so on the right side, if we want to try to keep those balanced, we could put a 5 over here. Our oxygens on the left side would go to 10. And we could put a 1 right here, knowing that our carbon and our hydrogen are already balanced. And so that would be our balanced calculation for it, or 1, 5, 3, 4. So next we look at doing conversions between 1 mole is equal to molar mass in grams, and then we also look at Avogadro's number, which is 6.02 times 10 to the 23rd. And for units, it's typically particles. It's usually regular units, molecules, or atoms. And they're going to try to, when you're going through the information or you're trying to do exam problems or something, they're going to try to interchangeably use molecules and moles and try to say that they're the same. They're not. If there is molecules, you're using the Avogadro's number to cancel that one out to get to another unit that you need to get to. So, for example, if we look at the first one, we're given 6.8 grams of NH3 would be how many moles of NH3. So we can use the conversions between molar mass in moles to get to that point. If we look at the molar mass of NH3, we should get 17 grams per mole. So we can see right here, this is what we're going to be starting with. And this is where we're going to be ending. So if you want to try to do a roadmap for yourself, we're starting at 6.8 grams of NH3, and we're going to moles of NH3. So we're starting with 6.8 grams of NH3, and we want to cancel. And if we remember a little bit ago, I mentioned that we can rewrite our 17 grams per mole in this manner, or we can write it in this manner. We have 1 mole is equal to 17 grams. And since we want our grams to cancel and we want to be left in moles, we would use this section option as our conversion. So we would have 1 mole of NH3 is equal to 17 grams of NH3. And if we were to plug that into our calculator, we're going to get 0.4 moles of NH3. So next, we're given a balanced equation, and we want to do what we're asked inside the question. So it says how many grams of sodium sulfate will be formed if we start with 200 grams of sodium hydroxide and you have been accessed to sulfuric acid. So anything that is highlighted is only the information that we really need. We can disregard the rest of it that it mentions. Even though that's great information for us, it doesn't really matter when we're doing the chemical calculations. So we're starting with 200 grams of NaOH, and we're going to grams of Na2SO4. So if we look at the molar masses for these first, so for molar masses for NaOH, you should get a molar mass of 40 grams per mole. And for Na2SO4, you should get a mass of 142 grams per mole. So if we look at the conversions for these, we're going to be starting in grams, and we want to end in grams of Na2SO4. So we're going to follow something like this, where we're going to start in grams of reactant, then we're going to go into moles of that reactant. We want our molar ratios. So if we look at the balanced equation, we can see over here that we have two NaOH to 1 of Na2SO4. So this arrow tells us that there's like an equals, like these two reactions equal to this. So we could use that as our converter exactly initially. So we could write it as 2 NaCl. So we could write it as 2 moles of NaOH is equal to, with our arrow being our equal, 1 mole of Na2SO4. But that only works if the equation is already balanced. So that is something we want to make sure we're looking out for and that we follow throughout the problems. So let's start. So if we're starting with 200 grams of NaOH, we want our grams to cancel first of NaOH. So if we have our grams, we can state it over here, is 40 grams of NaOH, which is equal to 1 mole of NaOH. Next, we want our moles to cancel. We want that molar ratio. So we can look up here, as I mentioned earlier, we have 1 mole, we have 2 moles of NaOH to 1 mole of Na2SO4. And so we want our NaOH to cancel and our moles. So we would have 2 moles of NaOH to 1 mole of Na2SO4. And then we want our moles to cancel because we want to end in grams of Na2SO4. So we could look at our other molar mass. And so we know that 1 mole of Na2SO4 is equal to 142 grams of Na2SO4. And when we plug all of that into our calculator, typically I tell students to run everything across the top first to get a value in their calculator, then run everything in the bottom to get a value in their calculator, and then do it all together, just so you're not trying to put 200 times 142 divided by 40 times 2, because that sometimes can get in some errors. And when you get that, you should get 355 grams of Na2SO4. So next we're given this balanced equation, and it's already balanced for us. And it says how many grams of lithium nitrate would be needed to make 250 grams of lithium sulfate, assuming that you have an adequate amount of lead for sulfate to do the reaction. So we know that we're going to be ending in how many grams of lithium nitrate, and it says to make. So we're going to be starting with 250 grams of lithium sulfate. And so if you want to draw out a roadmap for yourself, we know that we're going to start at 250 grams of lithium Li2SO4, and we're going to be ending in grams of lithium NO3. So if we look at the molar masses for both of them, we know that for lithium Li2SO4, we are going to have a mass of 109.90 grams per mole. And for lithium nitrate, we're going to have a mass of 68.94 grams per mole. If we look at the conversions for these, we're going to be starting with 250 grams of lithium sulfate. And we want our units of grams to cancel. So if we look at it out over here, we have 109.90 grams of Li2SO4 to 1 mole of Li2SO4. And we want that molar ratio to cancel. And if we look back at our balanced equation, we're looking at these two. So we have 4 moles of lithium nitrate to 2 moles of lithium sulfate. So when we're doing our balanced equation, we want our lithium sulfate to cancel. So we would have 2 moles of Li2SO4 to 4 moles of LiNO3. And then we want our units to cancel of moles, and we can look at our molar ratio. So we have 68.94 grams of LiNO3 to 1 mole of LiNO3. And when we plug that into our calculators, we should get an answer of 314 grams of lithium nitrate. So next we're given this balanced equation, and we're asked to calculate how many grams of iron can be made from 16.5 grams of iron oxide. I probably said that wrong, but I hope you understand what I'm meaning. So if we look at a map of what we're going to be doing, we're starting at 16.5 grams of Fe2O3, and we're going towards grams of iron. And if we look back at our balanced equation, we have 1 to 2 ratio. So that's what we're going to be using to cancel our molar ratio. But let's look at the molar masses for us. So for Fe2O3, we have a mass of 159.68 grams per mole. And for Fe, we have a mass of 55.84 grams per mole. And if we looked at how we're going to start this, we're starting with 16.5. We're starting with 16.5 grams of Fe2O3. And we want our grams to cancel, so we could look at the molar mass equaling 1 mole. So we would have 159.68 grams of Fe2O3 to 1 mole of Fe2O3. And with the molar ratio, we can see that we want them to cancel. So we have this 1 to 2 ratio. So we have 1 mole of Fe2O3 to 2 moles of Fe. And we want our units to cancel with moles so that we're ending in grams of iron. So we look at the molar mass, we have 55.84 grams of Fe to 1 mole of Fe. And when we plug that into our calculator, we should get an answer of 11.54 grams of iron. So next, we're given hydrogen is generated by passing hot steam over iron, which oxidizes to form Fe3O4 is in the following equation. So we're given this balanced equation, which is already balanced for us. And then it asks on the first one, if 625 grams of Fe3O4 is produced in the reaction, how many moles of hydrogen are produced at the same time? So we are starting with 625 and we're going to moles of hydrogen. So if we look at the molar masses for us, for H2, we have 2 grams per mole. And for Fe3O4, we're going to have a mass of 231.55 grams per mole. So we're starting at 625 grams of Fe3O4. We want our grams to cancel, so we would use the molar mass, so 231.55 grams of Fe3O4 to 1 mole. And then we only want to get to moles, so we just have to do our molar ratio, and then we're done. So we have 1 mole of Fe3O4 to 4 moles of H2. And when we plug that into our calculator, we're going to get 10.796, or you could round it to 10.8 moles of hydrogen. In the next one, we're asked how many moles of iron would be needed to generate 27 grams of hydrogen. So we're starting in 27 grams of hydrogen, and we're going to moles of iron. So for the molar masses for each of them, we're going to have for hydrogen, we're just going to have 1 grams per mole. And for iron, we're going to have 55.85 grams per mole. But since we're ending in moles of iron, we really won't need the molar mass of iron. So we're starting at 27 grams of hydrogen. And we have 1 gram of hydrogen equals 1 mole of hydrogen. When we look at the molar ratio, we can see that we have, in this case, we have a 3:4 ratio. So we have 4 moles of hydrogen to 3 moles of iron. And when that goes into our calculator, we should get an answer of 10.1 moles of Fe.